So this code helps you visualize rolling motion by giving you a disk made out of a wooden material here and keeping a tracker on the edge of it. So this red trajectory here represents the point traced out by 1 point on the edge of the disk. Now I've created this using a few different objects. First we have the disk itself. That's given by the cylinder function here. I've given it the wood texture. If you give it a solid color, you can't really see it rotating, but with a texture you can see the grain of the wood rotating. And basically we've set it up to where it will roll along the track here. Now I'm controlling the track length up here with this variable. That's going to control how long the thing rotates for. And then to get out the other parts of the visual, we've attached to the disk a rod. That's another cylinder function here. This is the white rod pointing from the center of the disk out to the edge of the disk here. And then we create a marker point. That's just a small sphere right at the edge of the rod, and that's going to keep track of the edge of the rod while the rod rotates around with the disk. And the important thing for the marker point is that we've turned on the make trail option. So we've set make trail equal to true for the marker point so that we can view its trajectory here. And so in the problems at the end of this video, you're going to be asked to create a second disk. Basically what you do is copy and paste the previous lines. I need to edit the line number there apparently. That is 13 through 28, into the space below, and you just make sure to give everything a new name. So you can call it disk 2, rod 2, marker point 2. Do make sure you rename all of them because otherwise it will overwrite the current one and leave it stranded over at the left-hand side. And then to set up the animation, we've set up a while loop that will run as long as the disk has not reached the edge of the track. So you can make the simulation run longer just by changing track length above. So for example, right now we've got a track length of 20 and we got out 1, 2, 3, and a little bit more of a revolution. If I change this thing, for example, to 25, I'll get a longer track and therefore a longer animation. So this time I'll get 1, 2, 3, 4 complete revolutions. Actually, just about 4. It doesn't quite reach another full revolution there. So I get just about 4 revolutions there for 25. But basically, this animation is going to continue as long as the disk is to the right of the edge of the track here. And the first thing we're going to do is update the angles. So they are going to update based on omega times dt. So you remember that to change something's position, you add to the position velocity times dt. Well, to update an angle, you just multiply it by you add to it the angular velocity times dt. And so we'll do the same thing for the disk and the rod. We're keeping track of their thetas separately just to make sure everything is up to date. And then we move the disk. We do that by updating its position based on its velocity. So this is just using the Euler-Kromer method. If you're still unfamiliar with the Euler-Kromer method, I'll leave a link to a series about it at in the description below. But this time the velocity, in order for this thing to roll without slipping, has to be given by the omega times the radius. So this is the velocity as long as this thing rolls without slipping. If you wanted it to behave like it was rolling with slipping, you would just adjust this value. So you might multiply it by, say, 1.5 or 0.5 or something like that to give its velocity a different value than omega times r. And then we're multiplying it by dt to get the time step, and a vector to the right just so that it moves to the rightward direction. And then we're actually rotating the disk. This isn't really part of the physics necessarily. This is just updating the visual using VPython's rotate function to rotate the disk about the appropriate axis by the appropriate angle. And then we need to move and rotate the rod and the point so that they stay in step with it. You'll notice that to move the marker point, we just update its position to be the rod's position plus the rod's axis, because the rod is rotating and moving along, so also the point needs to move and rotate along. And again, if you want to add a second disk, like you will in the problems at the end of this video, you'll need to copy all of this here and paste it within the same loop, and then update the name so that your disk, rod, and marker point also move alongside of this original disk. Now, the important thing you need to learn from this problem is the shape of this trajectory. This is a very special shape called the cycloid. It's the shape that a point on a wheel makes as it rolls along the ground without slipping. What you notice on this shape is that it's got a very unique feature called a cusp. You've probably heard about that in Calculus 1 or Calculus 2 and probably said, well, gosh, that's never going to occur in real life. Well, there it is in real life, a cusp. That's where the derivative, dy dx, is not defined, right? The derivative is nicely defined to the left, derivative is nicely defined to the right, but here, right at this moment, the derivative dy dx for that point is undefined, which is a pretty cool feature.